this episode, we would like to say that in the spirit of reconciliation, that we acknowledge the traditional custodians of country throughout Australia and their connections to the land, sea and community. Welcome back to another episode of Spaghettification. I'm the Drunk Astronomer.
And I'm Astronaut Duffy. Today we have with us Professor Alan Duffy from Swinburne. Professor Duffy simulates model universes on supercomputers to understand how galaxies like our Milky Way form within vast clouds of dark matter. He's trying to find this dark matter as the Swinburne node leader in the new National ARC Centre of Excellence for Dark Matter Particle Physics, and is the chief investigator of SABRE, the world's first dark matter detector in the Southern Hemisphere, to be deployed at the Stawell Underground Physics Laboratory. When not simulating universes, he tries to explain the science of this to the general public in regular segments on the ABC. Most recently, he's been appointed the inaugural director of the Space Technology and Industry Institute at Swinburne University of Technology. Finding ways to use space to help companies and communities here on Earth.
You made me feel exhausted just reading out that bio. I need to stop doing some of those things.
That's a big bio. There's a very big bio.
So our first question, Alan, you were born in England and raised in Northern Ireland before moving to Australia. Can you tell us a little bit about that and what drew you to Australia here?
All right. Well, certainly being able to grow up in Northern Ireland, not the most urbanized landscape, very much green fields, lots of small villages. And that meant that there were, at least when not cloudy, beautiful natural skies, no light pollution, and I was able to see the stars, and growing up was fascinated by them. In fact, some of my earliest memories is my face pressed against the cold glass of the car window looking out at the stars. But then also not just the stars, but that dark space between, and wondering, why it was dark. Is there because there were no stars? Is it because there were stars, but something was in the way? Or is there just something there but that we couldn't see, and actually turns out it's all three, and that was an early memory of a passion for astronomy. But I was fascinated more generally about everything in the natural world. I think astronomers do tend to be quite curious about most other aspects of our world. Geology in particular was a passion of mine, but then it really came to a head reading A Brief History of Time by Stephen Hawking. I was about 12 or 13. I since reread it, and I did not understand as much as I thought I did at the time. And then, in fact, I've reread it since, literally just a couple of years ago. And Stephen Hawking was wrong about one or two things, or at least the science, I should say, has moved on. He was right at the time, based on the understanding, particularly around dark matter. But so really, I found myself fascinated by this concept of becoming a cosmologist, because I saw that there was such a job title. Until reading that book, I literally didn't know that was a thing you could be. I went to uni. I got a PhD in simulating large-scale structure, which is what we term galaxies and the structures that are even larger. The cosmic web, the galaxies reside along and within, which are these vast dark matter structures. And then I, as everyone does at the end of their PhD, Steph, very much so, we can talk about this, but the mad job hunt around the world. You put in job submissions everywhere, and it just so happened that as I was putting in my applications, the Square Kilometre Array, the largest telescope that will ever be built, quite frankly, was proposed, was a very was unidentified. I'm trying to think, were we a finalist at that point, or was it actually given to us at that point?
I feel like we were finalists at that point.
I think that's right. Yeah, I think the final site decision and the split with South Africa came maybe a year or two later. But anyways, in anticipation of just the prototype for the Square Kilometre Array, known as ASCAP, the Australia SKA Pathfinder, we had astronomers from around the world pulled in to work in WA. So I got a role at Perth in the newly established International Centre for Radio Astronomy Research, led by Peter Quinn. So ICRAR was just this insane hive of activity. There were, dozens of dozens of astronomers now new to Australia were all sited in this brand new building. We're told this incredible vision of, let's see essentially every galaxy in the universe, or at least, all the neutral hydrogen and 1 billion plus galaxies back to the very observable edge of the universe. And this in this tracer. And, how can you say no to that kind of an opportunity? So came to Perth and just never looked back.
Well, it leads right into the second question, actually, because I actually did my research well for once. What was it like working on the square kilometre array? So, what did you actually do? What was your role, and what did you get from it?
Yeah, so my role was all around just that prototype, so ASCAP, which again is a so-called 1%. So it's in terms of collecting area, the square kilometre array is hundreds of thousands of telescopes put together, and if you add up all of their little bits of collecting area of the dish or dipoles, whatever, depending on the technology path, you get a square kilometre, and 1% of that is ASCAP, and even that was such an enormous advance. 36 dishes in the Murchison Shire, the Murchison Whitefield, the Murchison Protected Observatory, MRO. This site is pristine, no radio frequency interference, but we didn't actually know exactly what it could see. So the role that I had was, let's create a simulated universe, and then let's look at it, so to speak, with radio telescope eyes and see, quite literally, how many galaxies can we see? What sizes are there? Are we, and in particular, this is the key, are we biased? Are we getting a fair and accurate and faithful picture of the sky? Or, as is the case, are we preferentially seeing galaxies that are, say, face on rather than edge on? That's just one example. So we did all of this work, had the supercomputers humming in WA, worked with a very talented visualization team. In fact, Derek Gersman, Paul Burke, Peter Morse, on visualizing these simulations. So I'm still using the visuals. And in fact, we even made basically a planetarium show out of all of this. It was pretty cool, pretty crazy times. But in its heart, it was based around how can we optimize the surveys to better detect the galaxies we're interested in, knowing that there is a preference to see one kind of galaxy over another, for example. And really, you can only do that on a complexity and scale that even the 1% prototype version of the SKA is, using these kinds of supercomputer simulations. But before I could tackle the full SKA size program, I took up a role in Melbourne and switched fields a little bit. And certainly continue simulations, but for just different, very different era, actually, of our universe.
Well, I think that also then leads perfectly into our next question. So we've had to talk about your work
with that.
You've done very well.
I'm on a roll at the moment, question-wise. Sorry, I put all the questions together last night for this.
Yeah, okay.
I've somehow got it in order nicely.
You've guessed how boringly predictable I'm going to be. Is that what you're telling me now? Yeah.
No, not boring at all. Very, very interesting person, that's for sure.
So we've just discussed your work with ASCAP, which involved creating universes and supercomputers. So how do you actually go about this process? What do you learn when you create a universe in a supercomputer?
Mm-hmm. It's a great question. Let me maybe describe a somewhat idealized case, right? So the universe has a lot of stuff in it, atoms and dark matter, right? So those are the two matter ingredients. And dark matter only tracks, essentially only interacts, right, with gravity, whereas atoms are gravity plus what we call hydrodynamics, so pressure and interactions through emissions of light and everything else, right? So very complex additional laws govern that. So what you do in a simulation is you say, okay, well, here, my universe is a box. Don't worry, it's periodic boundaries. You can't leave the box. You come in the other side, right? So from that perspective, it's trying to represent a region maybe a few million light years across. You know what the starting point is because we have the cosmic microwave background. So this is the remnant afterglow of the Big Bang. It is a beautiful snapshot, and it tells you statistically exactly how stuff, dark matter and atoms, the gas, is distributed, floating around. So you start off with that picture with, in my case, little particles representing regions of space or mass. and you will have billions of particles in one of these cubes, and you can visualize that, and it literally is just a boring flat, distribution, right? It's almost completely smooth. There's tiny little imperfections, and those are the seeds of what will ultimately form galaxies. So gravity takes over, the simulation is advanced, and every you take a little estimate of the let's just talk gravity. So there's gravitational attraction between the particles because they have mass, so they have the force of gravity. They move together, and you basically solve that force. You move them together a little bit, and then you recalculate the force. So that's a time step. So you're stepping through the calculations, and you're literally seeing, maybe you do that every few thousand years, and then millions of years, whatever is the required accuracy. But what you see is these particles begin to slowly inch towards each other. But then as they pile in, they've got greater gravity overall, so they're able to pull in more material, and the whole thing accelerates and begins to snowball. And very quickly, you form large conglomerations of material that we will one day call galaxies. And in particular, the dark matter, and that's one of the first and key insights from these simulations. The dark matter falls together first, and it's gravity that acts as the gravitational backbone that pulls in the atoms that will one day form galaxies, and of course us. So that is the perhaps first insight that comes from the dark matter. If you don't put the dark matter in, you literally just don't get anything forming. Another insight you can get from the simulations, so in the instance that if you don't put the dark matter in, literally nothing forms by the present day. There's just not enough time in 13 billion years to form a galaxy without the accelerator, that is the dark matter. But you can then change the properties. So does that have an impact on the kind of galaxies that we see today? You can change the way that stars explode. In fact, it's a very important bit of physics that we can begin to explore in these simulations. So you're just playing with them, right? You adopt different laws, different rules, or essentially ingredients. And there's a lot more recipes you can tweak on the atoms and baryon side, as we call it. So the atoms and gas that form stars and us. That matter is a lot more than the dark matter. We're very much more complex than the dark matter at this point. So there's lots and lots of laws. And the last 20 years has been about trying to use these simulations and then compare against the real universe and see, are we able to explain it and recreate it? And if not, why not? And what does that tell us about the missing rules for making a galaxy? We are now getting to the stage where those rules are sufficiently well-defined and understood that we can then go the next stage, which is say, all right, well, let's go back to that dark matter and let's now change its properties. Maybe the dark matter is its own antiparticle, right? That's a cool concept from particle physics. Does that have an impact on what we see today? And can we then rule out that possibility because it doesn't match with reality? So in that way, we're able to use these simulations to better understand not just what we can see, but even the invisible component by its impact on the visible. So that's a wonderful stage of development, essentially beginning that pretty huge process of doing a whole series of simulations to explore all of those different kinds of possible universes and see which one best emulate looks most like our own.
So I teach third year physics at Bond Uni. One of the projects that my students do is they do a two-body simulation, so they have the Earth and the Sun rotating. Yep. And so that happens really quickly because, they're only running it for a few thousand years. It takes about 30 seconds. And then they put a third body in. So they do the Sun, the Earth, and Jupiter, and they get surprised that can take up to half an hour or so. So you mentioned that your galaxies and universe that you're simulating has billions of particles. So how long do these big simulations take to run?
Good. It is a good question. Quite a lot longer. We do have little tricks to speed this up. But yes, fundamentally, it is a huge computational challenge. So just we would run on a good chunk of an entire supercomputer. So we're talking anywhere, probably a few thousand cores, so a few thousand laptops that your students might be running, and be running that for easily 4 or 5 months. Some of the bigger runs have taken. We moved up to 1 trillion particles recently. globally now, and that took the world's fastest supercomputer, basically running for 6 months. And the challenge there is there's so much data you actually can't save what we call snapshots as you go, which is wonderful because you can then just sweep back in time and you can do lots of exciting things in terms of the understanding. When you have that much data, actually you can't save it, so you sort of you get the final picture and then you're like, oh, I really wish I could go back in the simulation and see what led to that structure for me. So some of this stuff is getting quite challenging computationally, and in fact most of the progress, I would say, in physics or astrophysics, is because we've been able to welcome in true experts in computer science, in data science, in engineering, rather than having astronomers trying to teach astronomers some coding. What we're doing is teaching actual real coders a little bit of astronomy context and welcome them into the community because they're much, much better at it. And that's the scale that we're at now as a problem. You just can't do this as an amateur. You've got to do it as a professional.
Best of both worlds.
Yeah. So once you've got this, 6 months worth of code run, how many people would really be working on that set of simulations? Is it one person job or is it many?
Yeah, absolutely. Ideally, many. Look, the tools are now sufficiently robust and user friendly, where you can pull up objects. You can. The images can be, in fact, behind me is an example, in fact, of one such galaxy, a little baby dwarf galaxy forming. Those kinds of renders used to take like a month of work to do it, and now it's just pulled up as an interactive plot. It's an extraordinary advance. So we can do a lot with just one person. However, the more people you have, the more science you can gain. So what we're now seeing is a drive to fewer but larger collaborations. So we have examples like Eagle out of Europe. There's the TNG out of US. We have a few different simulation series from Astro 3D, the Center of Excellence in Astronomy. That the simulations were led by Chris Power, for example, at UWA. So and that would pull in about half a dozen computer scientists or computational astrophysicists, and then we would have those interface tools such that potentially another dozen or more astronomers could get their hands on it and play with the data just as if it were real telescope data. So we call that mock observations, and that is now, in fact, this is freely accessible. You could go online right now to the website at Swinburne called TAO, so TAO, the Theoretical Astrophysics Observatory, and led by Darren Croden, and that you don't. The astronomer who uses it, it is completely generating image data cubes like a telescope does, but it's entirely simulation based. So you don't need to code at all. Right? And we've made those interface tools, brought the simulation to the astronomer rather than making the astronomer run the interactive tools. So that's a really wonderful advancement, but it is something that's only happened in the last few years. And again, perhaps just speaks to the maturity of the field. But ideally, the more people you have looking at these sims, the more science you're going to learn, and perhaps more bugs you may discover, if I'm being also honest. That is a wonderful advancement, but it's something that I can see only continue to grow, where very soon, in fact, one of perhaps the most productive simulation ever was the Millennium Simulation, which was back in 2008, and it's still being used, right? Because the tools were so good at analyzing it. The funny thing is, one of my students ran the Millennium Simulation on his own, just did it on the supercomputer, and was done within a few weeks. So that's how much computers have progressed too, right? This thing that broke Europe, took all of Europe to come together to make, and we still use it all these decades later, and Adam was able to regenerate it in a few weeks. So those are the moments where you realize Moore's law is insane. Yeah.
All of that goes over my head. It's not my area of expertise, but I do find it all very interesting. I'm learning a lot the longer I'm involved in the world of astronomy. That's for sure. Moving on from that, ARC Center of Excellence for All Sky Astrophysics in 3D and the ARC Center of Excellence for Gravitational Wave Discovery. You're involved in those as well.
Yeah, so for obvious reasons, we tend to describe them both by their acronym. So Astro 3D for the former and OSGRAV for the latter. These are so a Center of Excellence is a national 7-year funded program by the Australia Research Council, the ARC or ARC, and that is a vision outlined by the director for that center, and obviously, supported by senior scientists within this proposal. But the idea is, can we investigate something of global significance by pooling together all these researchers, giving them 7 years, giving them a lot of funding to just attack one huge problem? So the idea in Astro 3D was literally to explore the universe in 3D. So we tend to see these pictures of the sky, right? Dots along in a 2D plane. It's like, there's the objects. There's clearly a distance to them, but even more so than a distance, and that is, of course, is a third dimension. We actually have the spectra of those objects, and we can now explore their image, and then so we imagine a galaxy stretching in front of you, but then by looking at the color of its light in these incredibly thin slices of spectra, that's the rainbow color, you actually can see its motion. You can see the different material types within it. You can see, in fact, its accretion history by the different structures that get picked out. Literally, the fact that galaxies are cobbled together by infalling, or put it another way, graphically cannibalistically consumed objects. So you can begin to see in their time as well. So in that sense, the Astro 3D was about exploring this additional dimensionality of the data that the latest telescopes provided, and then provide next-gen simulations that make sense of that. So that's been a wonderful success. Arguably one of the big discoveries, in fact, was the fast radio burst, which is an entire new field of exploding something. Still don't know exactly what's exploding, but they're all over in the blink of an eye, literally in milliseconds. Fascinating objects, and that was a coming of age of that new phenomenon during the center. So that was wonderful. For OzGrav, in possibly some of the best timing of science since probably Louis Pasteur looked at a dish that he'd left out for a day or two. They basically proposed we should try to discover gravitational waves, and they proposed that just before they got discovered. In the process of the bid being considered, gravitational waves were discovered by the chance explosion of two ginormous black holes traveling for millions and millions of years, and the signal hits at that day. Absolutely extraordinary. Just a few days after the LIGO had turned on, after its upgrades, so we could finally see this. Extraordinary time of coincidence. OzGrav basically was just a shoo-in at that point, because this is a fundamentally new kind of signal to explore. So everything we do is electromagnetism. Even touch is fundamentally an exchange of virtual photons between our atoms of our fingers and that of the table, say. So it's still light, photons based. Gravitational waves are completely different. Nothing to do with electromagnetism. It's fundamentally, the vibration, the wave of space-time itself. So this is opening up our awareness of an entire new way of seeing, of listening, really. But it was a great proposal because this was clearly on the horizon. We just didn't anticipate it happening literally during the bid process. And what it has done since is detect numerous black holes, map out their demographics, really begin to probe their properties, set up just huge national, indeed international collaboration. So all of this work has been, quite frankly, extraordinary. They're going for their second round of funding, OzGrav 2, where that extends the vision yet further. So this is Matthew Bales at Swinburne, leads this. And that has just been, for me personally, such a deeply satisfying center to also be a part of. Astro 3D is my aligned to my science in terms of simulated universes, etc. But OzGrav is the one where I worried more about how do you visualize the fundamentally invisible black holes and explain the ripples of space-time, which is, to be honest, not something you can see either. So how do you do this as a faithful engagement tool and educational tool? And in that, we're very lucky to have Carl Knox as a visual designer, a computer scientist, kind of just this absolute genius science art guru figure. alongside with Mark on the tools, with the actual visualization and VR tools, all of this stuff coming together. Jackie Bondell, who's just an outrageous educator herself, then rolling these into classrooms. We've just had a bit of another wonderful bringing together of talent, just the right people with the right challenging topic. And you can get all of these animations and VR tools and everything else if you go to the Ozgrav website, including my own favorite Science in VR, which together with Katie Mack back in the day, and then Rebecca Allen, we did a few National Science Weeks. So yeah, these are all freely available. So just head to Ozgrav. Their website has a list of all the assets that you can download, play with.
Yeah.
Or Science in VR, the Cyber app is ready for your enjoyment on your smartphone right now.
Yeah.
I've got two of those cyber things, the headsets that you guys
the headsets are collector's items.
Yeah.
Oh, you don't get them.
Yeah, we've got two of those. The kids love them, absolutely love them. My daughter just every now and then she'll just steal my phone and put it in there and just have a go, wander around.
That's awesome. I'm so pleased that someone's still using them. That's great.
Yeah, seriously. No, we do. We sit on the shelf in the bedroom. They do. They definitely get used quite a lot. So it's a very, very good way of reaching the youth, I thought.
Well, look, in that regard, we're very much blessed with having Lisa Horsley in the team as well, who's done some incredible work at wrangling locations and, pub talks. We were in breweries for some of these shows. We were in going to museums, going out in incursions to schools and everything else. So, it's just one of those cases of just a really phenomenal team came together to deliver what I think is certainly Mark Meyer's work is, is downloaded over 10,000 times. It's the biggest app, as far as I'm aware, that's ever been done through National Science Week, which was part of the funding body for it. It was an extraordinary success. And clearly your daughter's still using it today. Well, that's awesome.
It was actually, it took Blake to see you when you did that at the State Library years back when it first.
Wow, that was the first. Oh my goodness.
Yeah, long ago. And we grabbed a couple of them, and so he's got one, and Sadie's got one now. And because of that talk and a few other bits and pieces, I mean, he's now he wants to get into that same field that essentially what you're in. That's his long-term goal. So,
all right. That's really pleasing to hear. It's often these things, and part of the problem with outreach, and I know Mark and Steph, you're both very experienced in this as well, is that unless you've got an actual in-person experience, it's very hard to get an immediate sense of feedback. Did it go well? Did people getting it or not? But regardless of even that, just longer term, have I made an impact? Have I changed the dial at all? It can be so hard to tell, and that's why it's so powerful. People take the time to send you just a quick email, say, "Oh, hey, I saw you at that talk all those years ago, and now I'm an astronomer, or I'm studying physics."
Well, there you go.
It really makes such a difference to hear those things.
I did that to Ivy Wong at UWA because I did work experience at Melbourne Uni Astro in 2006. And then when I was in Masters, I went to Hollywood, which is our sort of annual student conference. And she was one of the speakers. And I was like, "You were one of my supervisors there. And now I'm doing Masters." And she gave me a hug. I'd never interacted since then. But now I'm doing the work experience students, and I was looking at my desk, which is very messy. But I've still got notes and things from the work experience students that I've had over the years. And a couple of them, one of them is a master's student now at Melbourne Uni, and actually sent me her notes and things that she took during the week, in 2013. So,
that's extraordinary.
But you said, unless it's it's very hard to know actually if you're doing anything, but we still do it because it's fun.
Give an astronomer a hug, people. That's what we're saying.
Yes, please. I'm very cuddly. I've got this huge jumper on. You have had the opportunity to do lots of different talks, etc. We've talked about a few of them, but you've also been able to share a stage with a lot of different science communicators and things. What's it like working with these people who, we consider you our most famous astronomer here in Australia, but, people from the US, people from all over the world. What's it like working with these people?
Yeah, definitely. It's a case of being professional when you meet them and being like, okay, so here's the plan, and here's the stage floor plan, and here's the itinerary. But inside, going, oh my God, it's Brian Cox.
Yeah.
So yeah, and I actually knew Brian before, but I was still like, oh God. So I've had just an extraordinary opportunity with with Susie Jamel's Thinking. I was on stage most recently, just pre-pandemic. I mean, it's kind of insane, but 4 times with getting on stage.
BC.
What's that, sorry?
BC, before COVID.
Oh, before COVID, yeah. I thought you said BC, the initials of the person. I'm like, Brian Cox. But actually, that was through another agency. No. So getting on stage with people like getting to meet people and be on TV and stuff with Brian Cox, or doing the shows in particular. Most recently with Sean Carroll, that was Susie's Thinking, and that was it's. You have a duality of experience. You've got the moment where you are doing your job, asking the questions, checking on the audience, trying to keep things moving along, knowing where they want to get to, and knowing the science as well, of course. I mean, that's very helpful in that regard. I'm always interviewing people whose work I actually specifically know and researched, independent of the event. But then there's a second part of you watching the whole thing, just going, oh my God, I'm on stage with Neil deGrasse Tyson. This is weird. It's so cool. So look, what I found most incredible about them, and Jane Goodall is absolutely in this, is perhaps the most, wonderful example of this, but they all are incredibly, so is generous. Their generosity of their time with every one of those thousands of people that are in the audience. They would literally speak to every single person. They just would not leave. It's literally their mind just going, oh my God, you've been, you haven't slept now in 20 hours. I mean, I remember Jane just staying late because there was just a few extra people who wanted to see her. And, it's like by the end of it, the minder is panicking that you're going to collapse, but their generosity and their passion for communicating their science and engaging, and their humbleness about that. And I know it's not often a word used to describe Neil deGrasse Tyson, but he's very humble about the opportunity and the fact that the privilege of the platform and how important it is, and he takes that all very seriously. So when there was a chance to, I was backstage with him actually, and one of the people who worked behind at the convention center was like, just bring in like a water bottle or something. And he remembered this guy's name because he'd seen him the night before, and he told him something then, and he followed up. The level of focus that these superstars have on every single person they interact with, and they see every single person as a potential person to, positively influence with science, is just extraordinary. And it's something that, I hope I never forget that you've, if Jane Goodall is going to stay up for, 17 consecutive hours or whatever ridiculous amount of time it was, aged 80 plus, I could probably stay behind and give an extra few minutes to chat to people, right? And I think that's but it has been wonderful to learn from them about the way that they've share their messages or work in quite significantly amount of time in events to prepare really good, succinct descriptors of whatever the science is. And then they just have them in their back pocket. And that was very clear. I could see the same explanation being used a couple of times in separate evening events in different cities. Obviously, they'd been asked this before, but they'd really nailed the answer, and they'd clearly taken time to have that as sharp and clear and crystal clear as possible for the audience to get the most out of. That's what they'd done in their downtime, was to sharpen up this messaging. And I think that's also a reminder that what you see in those moments on stage is reflective of, countless hours off stage, doing the work, coming up with analogies, coming up with better ways of telling great science.
Is that like swinging string with things attached to the end of it?
Yeah, like I tried at ASB, just forgot to bring it. But yeah, that was I think Newtonian laws best understood by in-person demos.
I thought it was great. It was a really good way of showing the viewers exactly what you were trying to explain.
Yeah, I haven't had a chance to see if there were any comments on the YouTube stream, but
there's
someone enjoyed it. Yeah, okay, cool. All right.
Yeah. But you're right though. It's the little things that that these guys do that makes a difference to, I guess, their fans. And it doesn't matter what industry you're in. If so, for me as an architect, I got to meet a couple of my favorite architects over the years, and a couple of my favorite, one of my favorite comedians who's very much into architecture. And I went to quite a few of his shows in all these different sort of post-war modernist houses, and every single time I went there, he always did have a beer and have a chat about things. And it's just those little things. You didn't have to do that, but he did, and it makes the experience so much more exciting, and you remember it fondly, and you engage better with the history and with the journey.
Mm-hmm. Yeah, that's wonderful to hear. Who's the comedian, by the way, out of interest?
Tim Rosso. Very big into post-war modernist architecture.
That's okay. Yeah. Wouldn't have imagined that. That's cool. All right.
No, he's had a lot of TV shows on that field of architecture as well, and he does shows called Man About the House, and he travels around Australia and actually around the world now doing comedy shows in these historic post-war modernist homes that were designed by famous architects.
Wow, that is amazing to bring together two passions in your life.
Yeah, absolutely. Cool. And it's good fun because he's a funny man and he knows his stuff about the architecture as well. But it's just one of those things, like it's just the little things where he'll hang around after the show when everyone should have gone home and he'll just sit and talk to everybody as if you're hanging out with friends. And it's those little things that people remember and go, I want to go and do that again. I want to engage more with that.
And that's a responsibility you as an educator, as someone who, practitioner in outreach. I hesitate to call myself a science communicator. I'm very much a scientist who communicates. I haven't done the degrees or the training, professional training to be an actual science communicator. But the idea of this opportunity to positively influence someone versus negatively impact their view of that whole field of science, right? If you're a complete idiot to someone who's only just maybe getting into astronomy, that could turn them off astronomy, and what a horrible impact they've had. So I think it is a privilege, but it is a great responsibility that as well. And certainly, as I say, one that I know from personal experience, all of those huge names take as seriously as you might hope. But that was encouraging. I kind of thought maybe there'll be showbiz, but nah, they were just nerds. It's great.
So it leads into the fact that you wear a lot of hats in the world of science. One of those being the go-to man for the media. And I often when I talk to people about the things that you do, some of them will go, "Oh." So those who aren't in the world of astronomy or aren't interested in it will go, "Oh, who's Alan Duffy?" And I often go, "Well, he's Australia's answer to Neil deGrasse Tyson." That's the way I see. Okay. Yeah, no, honestly, that's the way I see is you are on that pedestal in Australia in the world of science and communication that he is over in America. You're the person that the media, from what I tell, tends to go to. So I want to. How did you get involved in that, and how much fun is it? Because every time I've seen you on TV, it looks like you're having a blast.
Oh yeah, I mean, well, let's answer that in reverse order. Yes, 100%. It's a blast. I mean, you're talking, on national TV about something that you're very passionate about. So for sure. But I think how it began was very organically, if I can use that word. It's by chance I was in UWA at the time. I was pretty late to science communication opportunities. It wasn't encouraged in Manchester just for whatever reason within my discipline area. Brian Cox is there, right? So as a university policy, very much considered a good thing. But when I came to UWA, Peter Quinn, who was the director of ICRA, was incredibly encouraging that we get out there, we talk about the science, we tell people about this incredible new facility that's coming, the ASCAP telescopes, and then of course the SKA and everything else. So I was beginning to do talks. I was really enjoying it. There was a radio producer was calling up. There was some event in the sky, and they wanted someone to talk about it. And I was there at work and got the call. I was like, okay, yeah, I'll chat. And I remember the now sadly passed away, but Russell Wolf. And I've got a recording, and I've chosen not to put it online because it's pretty bad. And it is a terrible interview. I am shockingly bad. I couldn't believe it. But the producers, within the ABC and WA at least, began to use me again. Personally, I think that was a mistake. It was terrible as a first interview, but with practice, you do get better, and eventually start to get TV, and it just began to snowball. And very quickly, I chose to have a bit of fun with it. I really like fashion. I like to look good in a certain way and have different styles. And I think it all went a bit mental when I was hitting the project, which is, $1 million+ audience. And everyone on the project is in a tie. And I was living in Fitzroy at this point in Melbourne, which everyone in Fitzroy was wearing a bow tie. So I was like, oh, I know, I'll wear a bow tie on TV, right? And then that was huge. And then someone pointed out to me, the science guy over in the US, Bill Nye, who does a bow tie, and I was like, oh no, I didn't realize. So I've since chosen to keep the bow tie as just a purely project thing, and anyways, I moved out of Fitzroy, and quite frankly, I could no longer get away with wearing that, so now I wear suits, which is very boring. But having that opportunity to go on TV for a few minutes, have millions of people potentially watching, and try your best to get across this extraordinary new thing, the context, the import, what's next, why they should care. It's a great challenge. It's such a thrill, but it's something that I'm constantly, still to this day, nervous about doing because of that fear again that I could turn someone off the science topic by just doing it badly, and hence I really do prepare for every interview just as much as I did when I first started this, right? I mean, it's just something that you don't take for granted, and I've done many hundreds, thousands of interviews, and if you include radio and TV together, but certainly several hundred TV interviews. Still take it real seriously, still have a little bit of nervous butterflies in the stomach. And if you don't, I don't think you're probably going to take it seriously enough. So I think having a bit of nerves is always good.
Absolutely agree. I was talking to a couple of guys at the ASV the other day, and I was just saying that because I did an interview yesterday at Caulfield for the new observatory. And by the way, thank you very much for that letter. It is,
I hope we get it. Fingers crossed.
Oh, so do I. It's going to be great. It was a few minutes of interview, and I was nervous as heck. And every time I host the ASV live streams or the monthly meetings, always nervous, butterflies in the stomach. And I say the same thing. If you're not feeling those butterflies in the stomach, you're not fully invested in it. You're not taking it serious, and you're not giving it the credit that it deserves. And because it's an honor to be able to stand up in front of all of these people and help them learn. And I'm not the one teaching them, I'm just the one hosting it and guiding it. But to be able to be there to guide the speakers and ask the questions and of the viewers, it is an absolute honor. And you've got to take it seriously. And I absolutely agree. It's a privilege.
I work in the planetarium, and even though my shows there are very basic compared to some of the talks that I've given about, galaxies in the universe, I still get a little bit like a minute or so before I start my talk of like, okay, these are 5-year-olds. I want to do a good job to make them excited about stars and things. And then you get into it, and you've got all sorts of visuals there that you can use. But even if I've done 4 of them that day, the 5th one I'm still like, okay, let's get this right. My question is now a bit about your maybe more recent work. Can you tell us a bit about your work with SABRE and in dark matter detection?
Absolutely. So this is a program led by Professor Elisabetta Barberio of University of Melbourne, both the Dark Matter Center of Excellence, but also Sabre. She's very busy. And the idea is the dark matter, through various astrophysical probes, we now have mapped out. We know where it is. We know how much there is, roughly 5 times more than everything we can see put together. And the properties, we think it's a new kind of particle, but we're not sure. So we're trying to investigate. And one way we might detect the dark matter is by its chance impact on an atom and ascending, very much snooker ball collision style, hitting an atom and sending it flying. That's happening in our bodies all the time, but we never notice it. However, with a very sophisticated detector called Sabre, we might. So the idea is that there is a crystal, very much, flask of bottle of water sort of size, ultra pure sodium iodide crystal that will flash a little bit of light when struck by the dark matter. We put 2 very sensitive cameras either side of that little flash-shaped crystal. They're called photomultiplier tubes, but essentially they'll pick up that little flash of light. We wrap the whole thing in ultra-pure copper because we're very worried about this detector can also see just anything that hits it, including naturally occurring radiation. So we need to make sure that we have only the purest of materials that are building the detector, because otherwise it'll just blind itself by itself, naturally occurring radiation. And all of this is placed within a large 10-ton vessel filled with liquid scintillator, which is an active background. But essentially the idea is that dark matter is a ghost, able to travel through the entire Earth without collision. So essentially, if it's traveling through the detector, and there of the billions of dark matter particles that will fly through, maybe one will hit the crystal and we'll get a little flash of light. And we'll look around and say, aha, did anything around that in the fluid that this crystal is immersed in, did it flash? And if not, then we're onto something, because there's just no chance the dark matter will hit 2 times in a row. But if there's a double flash, so in other words, a bit of radiation hit the liquid, traveled in, hit the crystal, then we know it can't be the dark matter. So 1 flash good, 2 flash bad. However, even with that active veto, the just naturally occurring radiation from space, known as cosmic rays, so exploding stars, feeding black holes, the sun itself, are hitting, basically there's a few hundred hits across your body each and every minute from these cosmic rays. So that would absolutely blind our detector, even with this active veto. So we have to take it deep underground, so 1 kilometer underground at the Stawell gold mine, now housed at the Stawell Underground Physics Laboratory, which is this like cathedral-sized thing that's been excavated 1 kilometer under the ground at the end of a long tunnel. There we place the detector and use that kilometer of rock above to act as a natural shield to stop the cosmic rays getting to us. The dark matter, again, it's a ghost. It'll travel through completely unaffected through that. So in that sense, we're trying to create this ultra quiet background, dark, no radiation, nice thermal controls, perfect, ultra clean environment, which is usually not what you associate with an active mine. So that itself has been a fun challenge. But essentially, we're nearing completion of all of this in installation. I've had the detector all through COVID, has sat in my Wantirna, Swinburne Wantirna campus lab. Thankfully, we're going to be able to deploy very, very soon, because for a number of us, we've been working on it for quite a few years of our life. We really want to start getting this detection running, and then we have to quietly wait and hope that we set up everything right, and then we'll be lucky enough that nature's kind enough that the dark matter will interact and hit our detector. And if it doesn't, we'll just have to build another bigger detector and keep looking. But that's the nature of science.
So that would be, if you discovered that, that's going to be probably the biggest discovery in the world of science, or would be.
Yeah, look, it's a Nobel Prize, that's for sure. It's not clear who gets it, but yeah, it's a Nobel Prize winning discovery. I don't think I'm in the running for it, but I think Elisabetta should have a fair case to be made for her to at least get a share of it. So, and partly the challenge is that there is a detection in the Northern Hemisphere by Dama Libra, an Italian detector, and that's in a place called Gran Sasso, which is carved out of a mountain So it's inside a mountain, so very Bond layer-esque. And they've recorded a detection for 10 years. The problem is no one else has been able to replicate that.
Yes.
And there is a worry that what they're seeing is something that changes through the course of a year, and that is known as an annual modulation. So annual year modulation changing. So the annual modulation is an expected signal of dark matter because, and hopefully just in the next minute I can explain this, but the idea is we have dark matter floating around the galaxy. Indeed, there's a halo of it that our galaxy resides within. And our sun, and indeed entire galaxy, slowly spins around. It's actually very fast. It's about 220 kilometers per second, but it's a big galaxy, so it takes 250 million years to do one revolution of our galaxy. So it means that the sun is traveling around and through that cloud of dark matter. And just as the individual air molecules are moving around at tremendous speeds, but unless there's a wind, bulk flow, motion of it, it's very still. There's no actual impact. Unless you're driving, right? And if you're driving and you put your hand out the window, you can feel the air push against you. But of course, I've just said it's a still day. So that's your motion through it that gives you that headwind effect. And in exactly the same way, we have our sun moving through the dark matter. Individual particles will be traveling at great speeds, but there's no bulk wind as such, but rather it's our motion through it, allowing us to be very confident there must be a headwind of dark matter reaching us. However, we're not on the sun, we're on the Earth. So for half the year, as our Earth travels around the sun, we go in the same direction as the sun. That means the headwind gets bigger. So we have more, stronger wind. We get more impacts expected in our detectors. And then for half the year, we go in the opposite direction. So the wind would die down, so we'll see fewer. And Gamma Libra has seen exactly that. More events in June, fewer events in December. The thing is, the other thing that changes in the year is the seasons. So perhaps what they're seeing, because no one else has been able to replicate this, is a seasonal impact. The easiest way to uncouple seasons is just to go to the other side of the world, where it's winter and summer are flipped, meaning we will see an opposite signal. We'll be 6 months out of phase with Gamma Libra if it's something to do with the seasons, because we have exactly the same detector technology as them, just a bit fancier, allowing us to do in 3 years what they've done in 10. But perhaps it is the dark matter, and we'll see more events in June, less in December if it's dark matter. But if it's something to do with the seasons, we'll be 6 months out of phase. And it's the cleanest way to rule in or out the Gamma Libra claim. So either way, we know we're going to get a result. But obviously, all of us are hoping we'll see dark matter. But even if we don't, we've ruled out a really important result and allowed the field to hone its search in a direction.
I had a really interesting talk from Inez Bigran, who's a research fellow at the Dark Matter Center, just about some of the things that go into building this. And so she was saying that because post-war, there's a lot more radioactive lead around because of testing of atomic weapons and things.
Natural fallout,
Yeah, so you have to use pre-war lead and source that to build some of these things because, again, you want to reduce as much contamination as possible. And it's just something I'd never thought of before, like it's such a sensitive instrument. You've got...
it's been, there's a Roman galley that was, sitting 2,000 years in the bottom of the Med, protected from that natural fallout, or it's not natural, but anyway, it was radioactive fallout, sorry. And I know that they went down and got the lead ingots. It was a trading ship, took the top layer off, gave it to the museums, and then melted down the lead to make the shielding for some of the Gran Sasso-based.
Amazing.
It's a lot of work, but dark matter is a really slippery character to try and pin down.
Yeah. They do say similar things with steel, with ships. The ships from the Second World War that were sunk. Quite a lot of them get pillaged for their steel for the same reason.
Yeah, in particular, there's the Scapa flow. So you actually need to get pre-World War II. So World War I, the German fleet was essentially, captured or interned at the Scapa flow, and they scuttled them rather than let the British have them. So now we have all that steel, high-grade naval, steel, uncontaminated by this fallout. So it's also a bit of a sad reminder that...
absolutely.
Nuclear testing is a really dumb idea.
Change the world forever.
It's a really dumb idea to do it anyway, but particularly on our planet, that seems really dumb.
Agreed. Now we've come to the last part of our interview where we try and embarrass our guests with a spot quiz on a topic that they most likely know nothing about. We interviewed Sarah Webb last week. Her podcast is about to go live. She got 3.5 out of 5 questions.
No, she got 4. She got 4.
So she got 4, didn't she?
Yeah.
Got 4 out of 5, right. And she said she would destroy you, that she would outdo you.
Very likely. I'm very bad at quizzes. I set them in my exams right at uni, but I'm terrible myself.
We made a mistake. Well, we didn't realise we'd made a mistake. We take the first letter of our guest's first name and choose a topic that is just so random and left of field that we assume they won't know anything about it.
Okay,
and
so
for Sarah,
astronomy.
For Sarah, I chose sea slugs. And
cucumbers.
Who would think that someone who spends their life in the world of astrophysics would know all about sea slugs? But she did.
Okay.
She did. Right. So for you...
Hit me. What's the A?
Armadillo lizards.
Oh, dear. Okay. All right. Well, that's over with. I can see this as being a 0-5, but we'll go.
I know we're fairly generous with answers. It's kind of... We give a bit of give or take. So we've got 5 questions. And they're all on different topics to do with armadillo lizards. So the first one is, an armadillo lizard's body can grow up to 10.5 centimetres in length. How long can its tail grow?
I want to say it's the same because they get to wrap themselves fully around. Is that okay? I don't know.
I don't think
10 centimeters.
Point for that one, Steffi.
What's the answer?
The tails can grow longer than their bodies and can measure up to 40 centimeters. So their tails can grow 4 times longer than their bodies.
Yep, no, that's a no then. Okay, next.
All right. So, what do armadillo lizards do to protect themselves?
Well, they curl up. They curl up in a nice little ball. So that one I know.
Yes. So armadillo lizards curl up into a ball to protect themselves. They stick their tails into their mouths and bat down. Then they present armored scales and hardened spines in all directions they might get attacked from. So they're basically Pokemon, I think.
Yeah, love it.
It's pretty cool.
That's one.
So we try and choose all these really weird things. So where do armadillo lizards live?
Okay, I think I've seen them walk on sand. So I'm guessing desert areas. Yeah, I guess I want to say, goodness, I couldn't even tell you what the continent is. Armadillos. I'm going to say, is it South America? Is it, we'll say, Chile? I don't know. I really don't. Is it got sand? I don't.
The south part and the sand was right. South Africa. And they live in the rock crevices in the mountain slopes and rocky outcrops along the western coast of South Africa.
Okay.
They do live on the beach areas, like the sandy beach areas, those rocky sandy beach areas.
I was thinking, is it more Spanish? Yeah. All right.
Second last question. So while they have very few predators, there are a few things that do threaten the lives of armadillo lizards. What are some of them that you can think of?
Ooh, well, if it's in Africa, I'm going to have to say wild dogs. I'm going to say snakes, maybe, and then people. I don't know. How am I? Have I got anything
pretty
right?
well, yeah. So we've got climate change.
Okay, right. The greatest predator of them all. The greatest predator of all.
That's people.
Exotic pet trade, which I think people fall under. And then invasive plant species.
Which people fall under as well.
Species. Oh, interesting. Yeah. Okay, cool.
Well, people fall under that as well because plants aren't going to invade areas unless we bring the seeds in.
Yeah, so I was thinking people, but more, for pet trade wise, or just being running them over or something, right? But yeah, I wasn't thinking people were hunting them. But
I think we can be generous and say we can give you a point for that one.
Yes.
So
all right. I've definitely been beaten by Sarah, but okay, let's limit the embarrassment with this next one.
She also has a podcast which is all about looking at random things on Wikipedia. So we probably could have planned better.
Yeah, well, I didn't realize that.
Yes. I also want to point out that we're talking about armadillo lizards and not armadillos, which you are correct, come from South America. So
I didn't know there was a difference. Oh,
yes.
Okay, well, you may take a point off me then. So I didn't know what I was talking about. All right.
Last question. How do armadillo lizards communicate with each other?
I seem to recall them having quite pointy noses, so I'm going to say lots of scent-based pheromone signals. I don't think do they have ears? I'm trying to picture them, but now it's not an armadillo, so I'm scared that an armadillo lizard is totally looking different now. Oh, I don't know. I'll say pheromones. I'll nail my colors to the mast on this one.
I'm going to have to say on that one. Armadillo lizards have many ways of communicating with each other: head bobbing, tongue flicking, and tail wagging of some of these methods. So they kind of, bob their head at each other or wag their tails like dogs, really.
They do look sort of like bearded lizards, if that helps you.
Yeah, kind of like South Africa's version of a bearded dragon.
Okay.
Yeah.
Well, that's not what I had
very
in my
cute.
mind at all.
They're very cute.
Okay, I'm going to look them up right afterwards.
They're very
Thank
cute.
you for sharing that with me. Now I have some homework to do. Yeah.
Well, that's the whole idea, because you know so much about your field of study, and the idea is to show people that if you put your mind to it, if you study hard and you focus on what you want to do, you can learn a lot, and you can become an amazing person in the field of study that you focus on. But it doesn't mean that you know everything, and you're just as human as the rest of us.
That's right.
Tragically.
On that very humbling note.
It's that humbling thing. Plus, it's a bit of fun as well. It's a bit of fun. Well, thank you very much for joining us on our, I'm calling it's still our fledgling podcast, because this is only episode 14. We're 14. And I know you did a podcast for a while too, because we used to listen to it in the car. Take one of the kids to school.
Yes. No, it's in much better hands now.
It was pretty good.
Carly Noon and Corey Tutt, who now host it, and it is exceptional. So please listen to the new and a much improved Cosmic Vertigo.
We'll promote it on our page as well.
Wonderful.
But thank you very much for joining us and for giving us some of your time. I know you're a busy man. So
well, I was going to say we haven't even asked anything about the space industry in Australia, so we may have to see if we can get you back at some point to talk about that.
Oh, absolutely. Yeah, no, happy to. All right. I'll speak to you then.
All right.
Cheers.
Thank you very
so much, Alan.
Thanks for listening and supporting us as we continue to learn on our podcast journey. If you would like to contribute to the podcast, you can head to www.patreon.com/Spaghettification podcast and support us for as little as 1 can of beer a day.